Hi everyone, my name is M.KRISHNA. In this video, I am going to explain silicon control rectifier two transistor analogy. Two transistor analogy of silicon control rectifier. Basically, we already seen that the structure of SCR. SCR is made up of four layers, four different layers, P and PN. So look at this. In this two transistor analogy, we are going to utilizing this structure of SCR to explain in brief the how that transistor is related to the SCR. Transistor operation is related to the SCR. We will see that. Look at this. This is my SCR structure PN. So here is my three terminals: anode terminal, cathode terminal, gate terminal. Three terminals are there. As we know, three junctions: J1, J2, J3 junctions. And we call this gate is the cathode gate because this terminal, gate terminal, is placed near to the cathode as compared to anode. So now what I am doing is I am going to split this part into two parts. Like this, look at this. When you make the mirror image of Z in the middle of the device, mirror image of Z like this, mirror image of Z like this, then we'll get the structure like this. Look at this. I am just splitting this part. So P comes as it is. P comes as it is. This NP, these two are going to be split into two parts. So one part is this one, the other part is this one, and N comes as it is. N is coming as it is, and this terminal is anode, this terminal is cathode, as same as here. This terminal is gate, this terminal is cathode, right? So I splitted this one into two parts. Then you just observe this one very carefully. So this is PNP. This is PNP. What does it mean? PNP transistor. PNP transistor. Look at this. This is NPN. NPN means NPN transistor. Means our SCR is formed with the help of two transistors. Two transistor configuration. One transistor is a PNP transistor. Other transistor is NPN transistor. So we are connecting these two in back-to-back manner. Back-to-back manner, we connected anti-parallelly, back-to-back manner. Look at this. So this is a figure number 1, figure number 2. Figure number 1 indicates the structure of the SCR. When this structure to divided into two parts, it will become like this. This is the figure number 2. So next, what I am doing is I am analyzing this circuit with the help of transistor model. This is my transistor model. This is my transistor model. Look at this. This is my PNP transistor. This is my PNP transistor. So look at this. How can I represent this PNP transistor? So this is arrow mark indicating inverse to the device. Inverse to the device means if N is there in the middle, means then only we can show that PNP transistor like this. Arrow mark towards to the base that indicating the PNP transistor. If arrow mark coming out from the device, from the base terminal, from the base, that indicates the NPN transistor. So this is the transistor model for SCR. This is what I'm calling this SCR as Q1. I'm calling this SCR as Q2. And look at the different types of names are given for the different currents. Look at this upper portion. This is my anode. This is my anode. This is my anode current. Anode current. When you consider this as a transistor, this is my emitter. This is my base. This is my collector for this transistor. Okay, and I can say this current, anode current is same as emitter current. I can say this as E1 means current flowing through this emitter is IE1. So I can call this IE1 is equal to IA. Like this is my collector C1 current coming out from collector terminal is IC1. current coming out from base terminal is IB1. This is regarding to transistor 1, and coming to transistor 2, this is NPN transistor. So these two are connected in anti-parallel back to back connection. So this is my collector. So this is my collector, this is my emitter. This is cathode terminal as per as SCR concern. Okay, this is cathode current. This is emitter 2 current, emitter 2, IE2. IE2 is equal to IK, cathode current. And this is this connection is like this connection is like this coupled like this, means IB1 current also flowing to the collector, into the collector terminal of the transistor Q, means what? IC2 equal to IB1. And look at this. So this is the KCL portion. When you apply KCL here, so we will get one equation. Look at this fourth diagram. This is our basic SCR symbol. This is my anode current. This is my gate current. This is my cathode current. From this diagram, what we can write, when you apply the KCL to this device, you can get this is current out from the device. This is inwards towards the device. This is also into the device. So what we call, when you apply the KCL to this device, then you will get equation like this. IK is equal to the IA plus IG. Like this, we'll get the equation. Now we'll see how this is going to be happen, how the operation is going on when you analyze the SCR operation in terms of transistor analogy. Okay, so we'll see. Common base current gain of transistors. See, I have two transistors here, Q1, Q2. Now I am taking common base current gains of two transistors. I call current gain of this Q1 is alpha 1, current gain of this Q2 is alpha 2. What do you mean by current gain? Current gain is the is defined as the ratio of collector current to the base current. Alpha is equal to IC by IB. When you take the transistor configurations, three different types of configurations are available. So one among them is common base configuration. In the common base configuration, we can able to see alpha value current gain. Current gain is taking in terms of currents. See, IC upon IB. Okay. See next. Look at this. Here we have a node point. When you apply KCL to this node point, you will get IB2 is equal to IC1 plus IG. Look at this. This current is entering. This current is entering into the node, but IB2 current is leaving from the node. Then I am applying KCL here. Thereby I am getting IB2 is equal to the IC1 plus IG1. As same as that, I am applying KCL here to the transistor Q2. Then I am getting IE2 is equal to the IC2 plus IB2. Look at this. This current is entering. This current is entering into the device, but this IE2 current is leaving from the device. Then there also for the Q2 I am applying KCL. Then I am getting like this. Then in place of IB2 I am just replacing these values. Then IC2 is equal to IC2 plus IC1 plus IG. This IE2 is nothing but IK. This is IK. Now I am replacing all the terms. This is IE2 is nothing but IK, IC2 plus IC1 plus IG. Okay. From this, we have one more equation in terms of collector currents. That is, when you apply Q1, that is IC1 is equal to alpha I1, IE1 plus ICO1. Look at this. This alpha 1 is nothing but current gain of transistor Q1, and this is ICO1 means this is a collector linkage current when the operation is going on. So we are writing collector equation in terms of these factors, and I am applying the same thing for the Q2 and getting equation like this. IC2 is equal to alpha 2 IE2 plus ICO0 ICO2. Okay, then now what I am doing is this IA2 is nothing but IK. This IA2 is nothing but IK. Yes. Now look at this. IK is equal to IC2 plus IC1 plus IG. Okay, I know that IK. I am replacing that IK with respect to IA plus IG. Then I am getting IA plus IG is equal to IC2 plus IC1 plus IG. Am I clear now? Look at this. This equation I got. IK is equal to IC2 plus IC1 plus IG. From this, I am just replacing this IK with the model of SCR. When you apply KCL to the SCR, then I am getting equation like this. IK is equal to IA plus IG. Then I am simply replacing the IK with respect to IA plus IG. Therefore, we are getting equation like this. This IJ I should cancel out. Then I am getting the equation like this. IJ is equal to IC2 plus IC1. This is the reference equation which you have to follow on forward. Okay? We know these two equations. This one equation, with the help of these three equations, we are going to analyze the next part of the topic. Now, I am simply replacing that IC1 and IC2 there. Alpha 2 IE2 plus ICO2 plus alpha 1 IE1 plus ICO1. Simply replacing that IC2 plus IC1 with their respective values in these two equations. Okay, let's we'll see next. Alpha 2 IE2 means this IE2 which is equal to IK, but IK is equal to IJ. Now IE2 is replaced by IK is replaced by IA plus IG plus ICO2 plus alpha 1, then IE1, look at this. This is IE1, this is IA. IE1 is equal to IA, and I am replacing with IA1 with IA plus ICO1. So this side is IA. Now take all IA terms to one side. Then IA of 1 minus alpha 2 IA, alpha 1 IA. Alpha 1 plus alpha 2 equal to ICO2 plus ICO1 plus alpha 2 IG. So finally we will get equation. Now final equation for this IA current, then IA is equal to ICO2 plus ICO1 plus alpha 2 Ig upon 1 by 1 minus of alpha 1 plus alpha 2. This is the final equation for analyzing the SCR operation in terms of transistor model. Okay, this is very clear. So terms are very clear here. ICO2 is the collector leakage current regarding to transistor Q1, Q2. This is the collector leakage current when you consider the Q1. This is the IG gate current. This alpha 2 is the current gain of the Q2 transistor. Okay, in other terms, this is IA anode current, which is a very important current for our SCR. Now, how do we increase the operation? How do we increase the current flow through the device? How do you make the SCR into on state? Very simple, normal general analysis we already seen in the previous class. But what we discussed in the last class, look at this. If IG current increases, if Ig increases, Ia increases. If Ig increases, Ia increases. Means if you apply the gate voltage across the gate and cathode terminals, when you force the current through the gate terminal, J2 junction will break down earlier so that it allows the current to from anode to cathode. That is the concept. Means what here also same thing. If you increase this Ig value, if we increase this Ig value, this current must be increased. The current flow from anode to cathode must be increased. When it is happen, look at this. When this total term comes to 0, then only it happens. When alpha 1 plus alpha 2 becomes 0, then only it happens. Okay? How do you make this? Very simple. If J2 junction, if J2 junction, width of the J2 junction increases, point is width of J2 junction increases, alpha decreases. Alpha decreases. If width of the J2 junction increases, alpha decreases. This is the concept. So when this happens, automatically alpha values are reduced, and vice versa. Suppose when it reaches to 1, then automatically IA current increases. So once this IA increases, so look at this, IA is equal to ICO2 plus ICO1 plus alpha 2 Ig. This is my equation. After that, alpha 1 plus alpha 2 reaches to 0. Then these two parameters are leakage values, leakage currents for the both transistors Q1 and Q2. Thereby, I am simply neglecting these values because of leakage currents. So we have equations IA is equal to alpha to Ig. Alpha to Ig, current again alpha to Ig. I can say IA is directly proportional to Ig. IA is directly proportional to Ig. If Ig increases, automatically Ia increases. Then SCR comes to on state and allow the current to flow anode to cathode. So this is the total about the transistor analogy of SCR. So it is very important analogy, and the next we will see SCRs. We already seen the static characteristics of SCR. We will see the dynamic characteristics. So dynamic characteristics means on time, off time. two things are there. We'll discuss that dynamic characteristics of SCR in the next video. Thank you.